So modern programming languages are incredibly powerful, but they don't learn or adapt from how people use them. In this work, we're imagining what a programming language looks like when it can learn from how one programmer uses it to then help other programmers. So one key idea here is that for most programming languages, a lot of implicit knowledge builds up over time in communities of users. This knowledge exists on Q&A sites like Stack Overflow, online tutorials, and open source libraries, among many other places. So these community resources are powerful, and one common goal of many tools for software development is to help people write code using the knowledge that exists in these communities. For example, Joel Brandt's Blueprint work embeds search for common code snippets into an IDE, and our earlier work on Codex annotated users' programs with statistical patterns we mined from open source code. These kinds of tools link community resources to code, which is great, but these links only go in one direction. Code can benefit from community resources, but the community resources don't generally learn from new code. So one really interesting question to ask is, what if we had a link going in the other direction? What could we do if community resources learn directly from the programs people write? Bjorn Hartmann's work on Help Me Out explored this idea, allowing a community of programmers to learn from how other programmers fix runtime bugs. This was really powerful, but limited to bug fixing. Our work is asking, what new language features could we design with a full bidirectional link, where community resources both inform and evolve with users' code? What would a programming language look like if it could learn from how people use it? Meta is our first attempt at instantiating this idea. It's a language extension for Python that allows users to share functions and records how people use them. The implication of all this is that community-aware programming languages enable many new kinds of interfaces. With Meta, we demonstrate examples of, say, better code search, taking advantage of argument types and examples. Or optimization, leveraging community code to make your program faster. Or code patching, which swaps in community code to help your program recover from runtime bugs. Or better forms of automatic documentation informed by argument types and examples. Or finally, proactive linting, which warns you when your code fails anywhere else in the community. But probably the best way of introducing you to Meta is through a live demo. Switch this up. Cool, so first let's import a few things. And now, at its core, Meta is about sharing functions and recording the different ways that people use them. So there are really two typical ways a user will interact with Meta. The first is registering an existing function that they've already written with the community, basically turning a normal Python function into a Meta function. So we can do this by adding the Meta decorator to a Python function along with an optional documentation string. And so what this will do is transform this function into a shareable community function with a unique community URL. So here I'm going to print out the URL for this function. This function, by the way, takes the name of a company and returns the stock price for this company. So we'll print this out. And so if we follow this link, we can see an example of a typical Meta function. So there's some basic information like a description of the function. There is the source code of the function and a type signature for the function, which it doesn't know right now since we haven't used this function. We just created it. So switching back. And now that we've created this function, basically let's give Meta an example so they can start to learn something about it. So, for example, let's look up the stock price for Toyota. So they seem to be doing pretty well. Now that we have this example that we've given Meta, we can ask it to basically infer a type signature from that example. And so this is really useful both as a form of documentation in terms of figuring out what a function does, but also as a lower level API for Meta itself. So here we can see that the function is taking a string, the name of the company, and producing a float, which is the stock price. So with Meta, it's also possible to ask any function to produce examples of how it's been used. And this can be another really helpful form of documentation. So here, let's ask the getPrice function for an example. And kind of unsurprisingly, this is the input we just gave it, since this is the first time this function's ever existed or has been used. So another nice thing that Meta will do is record and centralize information about exceptions or bugs. For example, this function might break if we pass it a string that's too long for the API to handle. So in particular, if we pass it, say, a string of 1,000 A's, we can try to run it. And so that breaks. So then anyone else in the community can basically ask this function, when have you broken? Like, what's gone wrong with you through Meta's API? And then we see this exception. It's great, right? Like, very informative. So cool. So I should say here, in practice, it may not be convenient to call all these APIs outside of an interpreter environment. So a more common place to find this kind of information is, again, the functions community webpage. So if we go back to that webpage that we saw earlier, which was kind of empty, if we look at it now, we see that we have the example that we called, and we also see the bug. Similarly, we see the type signature. But beyond creating these meta functions, another super common thing you want to do is load and use an existing function from the community. So in general, you can do this by loading any function given the URL of its community webpage. For example, here's a function that merges two dictionaries. So if we follow this link, we can see what function we're dealing with. So we see, yes, we're merging two dictionaries in a single expression. In particular, we're using itertools.chain. We see a type signature, takes two dictionaries, returns a dictionary. Also see some examples from the community. And you can also load functions by searching for them, both in code and on the community website. What's interesting here is that a sort of deep integration of Meta with code allows you to do some advanced kinds of search. For example, searching using an example input and output. So here we have two dictionaries, D1 and D2. D1 has keys A and B, D2 has key C. And we have O, which is what we might expect the merging of these dictionaries to be with inputs and output. And so we can pass Meta this example and ask it to find a function that basically conforms to that example. And so we see a link that it found. So beyond all of these relatively simple APIs, Meta also has some advanced functionality enabled by its ability to find equivalent functions from the community. So for example, if you can find an equivalent version of a function that's faster, you might use that to, say, optimize a function. Now, this is a lower level API that Meta uses, but we can still call it here on our dictionary merging function. So we're going to ask this for equivalence. What this code is going to do is basically print out the URL for the original function, and then for any of the equivalents that it finds, it's also going to print out the URL for those equivalents. Yeah? Okay. So we can follow this link. And so here we see another dictionary merging function. It's a little bit different. It does a different thing with update. Again, some examples. Again, type signature. So right now I should say we do this through a very expensive automated form of dynamic analysis, but we're looking at sort of relying on community curation for this sort of thing going forward. And what's cool about this, though, is it enables certain kinds of things, like optimization. So say we want to find the fastest version of this dictionary merging function. We can ask Meta to optimize it. And so what this is going to do is find all the equivalent functions, test them out on a sample of inputs, and basically choose the one that does best. And so we can see from this, apology for the screen size, but so we can see from this it found something. And it's going to store that in the variable opt. And now we can ask basically, like, given some manual testing code, is this actually faster? Just do a little sanity check here. So here's some example inputs. Here's the original dictionary merging function. Here's the optimized function. So we can run this. We see the optimized one is actually faster. And so one final last thing is that with this find equivalence, we can also do some cool sort of runtime saving stuff. So remember that our get price function failed when we gave it an input that was too long for it to handle. Let's say someone else in the community is writing a similar function. They're a little bit smarter than we are, so they put in this check here to basically check whether the company name is too long. If so, just return none. Otherwise, do the same thing. And so they do that. So we don't need to know that anyone else has done something better than we have, but if we ask our function to sort of auto-patch itself in case it hits something bad, in production or something, and then we run this. So what will happen is we'll hit the same exception we hit before, but it will sort of try to find a fallback option using any other function in the community. We'll get a warning that says it was auto-patched with this other function, and then returns none instead of throwing an exception. So with that, let me move back to some more details about how this stuff works. Cool. So earlier I asked, what would a programming language look like if it could learn from how people use it? Through Meta, I hope you've seen how such a language can begin to enable new forms of search and documentation through types and examples, or new interfaces for optimization and runtime patching, given community code. So these are all enabled by Meta's ability to share code and track its use across a community. And now I'd like to say a bit about how we built Meta, starting with Meta functions. So as you saw in the demo, Meta functions are callable Python objects that enable a range of new interactions. They're stored and loaded from a community database and will record their runtime behavior. The way this works is that when a new function is created, Meta records the name of the function, the source code of the function, and any importable libraries the function requires. Together, these properties allow that function to be loaded dynamically from the database via meta.load and used in another programmer's code. To make this kind of distribution possible, these functions can't use global state besides library imports, and we detect and avoid running functions with I/O by instrumenting core system libraries. We also cache functions locally to speed up things and allow Meta to work without network access. Similarly, knowledge about community functions grows over time as Meta functions are executed. So at runtime, Meta will record the arguments passed to a function, the return value of the function, the types associated with a function's argument and return value, how long it takes the function to execute, and any exceptions the functions encounter. These data then collect in a database and enable the APIs I went over earlier. Because sampling all the data that passes through functions would add significant overhead to Meta programs, we record data probabilistically at a rate of 1 over n, where n is the number of times the function has been called. So for functions that are called very frequently, in the inner loop of a large for loop, for example, this is critical for maintaining good performance. And now let's step back and talk about how we evaluated Meta. So in our first study, we hired 7 programmers from the Upwork platform to use Meta to complete a machine learning classification task. After each programmer finished the task, we interviewed them and examined their code to better understand the strengths and limitations of using Meta. So all programmers successfully completed the machine learning task. In total, they wrote 746 lines of code, of which 26% was covered by Meta functions. They also created 17 Meta functions, loaded 6 unique Meta functions, and executed functions more than 15,000 times. The functions they loaded tended to be utility functions like bool to int or flatten list, while the functions they created tended to be more complicated, for example, transforming a document into a vector. Finally, when we interviewed the programmers, they raised a lot of points about security and privacy, as well as how we can grow the community, which we're using to inform Meta's design going forward. So our second study evaluated, in contrast to this, sort of the overhead of Meta functions, as opposed to running traditional Python programs. So some overhead makes sense here, as Meta is downloading code across a network, as well as recording and introspecting function inputs. So we took the 7 programs from the previous study and evaluated the cost of loading, creating, and executing these functions, as opposed to a traditional Python baseline. So we found the average time cost of loading a Meta function was 47 milliseconds, and the cost of creating a function via the decorator was 133 milliseconds. So these costs reflect the fact that Meta needs to evaluate a stored function's source code, or else save it in the case of function creation. And these are fixed costs that only occur once per function per program execution. So on average, actually calling a Meta function only added 0.31 milliseconds to a normal function call. And finally, our last study examined the potential benefits of function optimization. So we ran Meta's optimizer over all code in the community, manually examined all suggested optimizations for correctness, then calculated the distribution of performance improvements. So in total, Meta found 44 correct optimizations and 7 incorrect optimizations. The median optimized function was 1.45 times faster than the non-optimized version. And you've already seen an example of when optimization goes right, but when can things go wrong? Meta's mistakes were generally caused by data sparsity. For example, the function is capitalized had been observed on only one runtime argument, ABC, which produced the result false. When ABC was passed to a possible equivalent function, string is number, the second function also returned false, leading Meta to conclude that string is number could be used in place of is capitalized. So these mistakes disappeared when we added new runtime information to the system. For example, after we called is capitalized on hello with a capital H, Meta no longer suggested the faulty optimization. Now, finally, I'd like to talk about future work, because there's a ton to do here which this paper has really only begun to address. And in particular, one big open question is, how does a system like Meta scale to a community with a much larger number of users? Could we make something like the Find Equivalence API work under something like community curation? And what other kinds of community dynamics emerge? Another important question is, what kinds of features can we design when programming languages are able to explicitly draw from the code written by their users? Meta is capable of some additional functionality which I didn't touch much on in this talk, like testing a function automatically on community inputs. We also have some early experiments which show promising results for program synthesis. But what other functions or what other features could we create? And is it possible to evolve the ideas of Meta to support programs with more complex global state? A lot of modern code isn't written in the form of pure functions, and it would be really great to support this kind of stuff. So in this talk, I showed how connecting code across a community can enable programming resources that benefit from a much richer swath of runtime data, and how tools can use these data to help programmers write better code. Looking forward, Meta envisions a world in which an enormous amount of data about how people program is introspectable and available for analysis, making possible a new class of intelligent programming environments. So check out our webpage if you're interested in playing with the current beta, and thanks, and I'm happy to take any questions.
Thanks, Ethan. Questions? Seems like we have one.
Hi, I'm Ken. Really nice work on programming on the function level. Wondering if you've thought anything about how you could apply any of these kind of ideas to perhaps more large-scale changes, like, for example, suggesting a different kind of data structure that might be an order of magnitude or order big O notation faster than what could be possible with the data structure that was already there. Or perhaps programming in the medium or large, not just programming in the small.
Right. Yeah, that's a great question. And yeah, we've definitely thought about that. There's a sense of which sort of collecting more metadata about a function, in particular some of this natural language data or this sort of type signature data, can allow you to sort of reason about, like, when I say I want to do something, can I figure out, my intent and then find other functions regardless of this type signature that match that intent? You can also imagine doing a kind of like clustering of type signatures to figure out things that are, very similar but not quite the same, and then saying like, hey, this one over here does this thing a lot faster, but, you need to use a different type. And so then suggesting maybe a transformation of type. Yeah.
Awesome work here. How easily do you think that this translates between various programming languages?
So you need some amount of sort of ability to introspect, and Python's reasonable at that. It's certainly not the only programming language that does that. If you wanted to take something like this into like the Haskell world or something, that would be much, much more difficult. Functions like would have a harder time. I mean, maybe if you're using like template Haskell or something, but like in general, be more difficult with statically typed languages that really have to, not modify themselves and whatever. But any of the class of functions that is kind of key to modern web development, I think would be a good fit.
Seemed like there was a question there.
Hi, Michel Baudon-Lafont, Université Paris-Sud. Have you thought about how you could use this to clean up all the community stuff, because Stack Overflow does not always give the best advice?
Yes. Yes, so that's, I didn't actually mention this, but our community is largely composed of Stack Overflow functions, in the sense that, to bootstrap this thing, we had paid freelancers go out to Stack Overflow, collect every possible thing we could suck into this community, and then when we're talking about, say, doing the optimization analysis, like, there's a lot of duplicate stuff. Even though Stack Overflow has like a mark as duplicate button or whatever, like, we were able to find a lot of duplicates, and some were much better than others. Also, in the course of having these freelancers do this stuff, they were often coming back to me and being like, hey, this is completely ridiculous. Can I just like do this the right way instead of the way that the correct answer has it on Stack Overflow? So yeah, definitely a big issue.
Actually, just to follow on that question, when I was playing around with it, I felt like this would be a great way to cheat on a technical interview. Do you have any comments?
Probably the technical interview should just be like, don't use Meta. But yeah, good point.
Yeah. It seemed like there was one last question. Okay. Oh, go for it. Oh.
Oh, okay. Cool.
No.
Yeah. Oh, well, I can say more if you want. So basically, the ability to find equivalence is, somewhat sketchy, in the way we define it. You can look at the paper if you want to see specifically how we defined it. So that's like certainly not like a clear thing. But between all these different signals that we have, sort of like the natural language signals, the dynamic analysis signals, the community curation signals, like we're sort of hoping that that's at least better than what Stack Overflow has, like if you have a real community. But it's certainly impossible. It's sort of mostly impossible in a theoretical sense to actually like know for sure that you're cleaning up all the duplicates. Sure.
Any final questions? Awesome. Thank you, Ethan. This concludes the DevTools session.